So this is kind of a fun two-dimensional kinematic problem that requires actually the use of a trig identity. So we're going to set it up. So if a ball is launched at ground level with an initial velocity of 12 meters per second, we know it travels a horizontal distance of 12.71 meters, neglecting drag. What is the angle of the ball, or what is the angle the ball must be launched from? So let's use our problem-solving method to set this up. What is the thing I am looking for? I'm looking for the angle of launch, which we can just call theta, representing an angle. And I'm going to kind of draw an image of what this looks like. So we have a ball from ground level, and it is going to have some initial velocity. And this is going to be the angle of launch. It's horizontal distance. This is going to be 12.71 meters. And its height, we can call the y initial is 0. Right, so it's launched off the ground. The input, or the numbers I'm given, are v initial is equal to 12 meters per second. If I know it hits the ground, I also know v final. It's going to be 0 meters per second. That might come in handy later. The change in horizontal distance, so I'll represent that just with the letter x. To denote its horizontal distance is 12.71 meters, and we know that gravity is 9.81 meters per second. Now I could account for the direction of gravity. So gravity, the acceleration due to gravity, acceleration is a vector, direction does matter. So either I account, and gravity is going to accelerate something downwards, either I account for the direction in the data point or I account for it in the equation. My personal preference is to do it in the equation. So I'm going to call it positive 9.81 meters per second squared. But really what I'm saying is we need to account for that direction at some point. So that's going to be important. The equations I'm going to use are going to be 3, really. I'm going to use that the velocity is equal to the change in distance over the change in time of an object. For this case, because time is a scalar, I'm just going to call it and denote it as t. Knowing it's just a scalar, I'm just taking time as it passes. I'm going to use a kinematic equation. X final is equal to x initial plus v initial t plus 1/2 at squared from the kinematic equations we've been using. And I am going to use one more equation. This one is one that you are not familiar with, but this is a trig identity. The sine of 2 theta is equal to 2 sine theta cosine theta. Now, I know I need this partly because I wrote this problem, but actually the main reason I wrote this problem, but this is a double angle identity. So if you didn't know you needed this right away, you could figure out later when we'll get this term sine theta, cosine theta, and you'd be like, well, how do I solve that? Trig identity. So that's how you would eventually find out you knew you needed it. Let's do our solution set then. We're going to start with anything we can kind of get to get us theta. And in this case, because I know the change in the horizontal distance, I'm going to set it up as the horizontal component. So the velocity in the x direction, that's going to equal the change in horizontal distance over time. Okay. The velocity in the x direction needs to be expounded using sine, cosine, tangent. It's the adjacent side of the whole velocity component of that angle. So I know that the cosine of theta, whatever the angle is equal to the adjacent VIX over the whole vector VI. We've learned in our vector analysis in the math review. So if I'm just solving for VIX, I just multiply the initial velocity to both sides of the equation. So I get the initial x velocity is equal to the velocity, the cosine of theta, and that is equal to the change in position over time. Now I could divide one of these over to the other side, but you'll notice I have time, which is something I don't know, and I have theta, which is something I don't know. So I currently have one equation with 2 unknowns, and that just by itself isn't solvable. So this is where this middle kinematic equation comes from. And the way we're going to use this is, so once the ball gets launched, there's no horizontal component of acceleration, right? It's not touching anything. We're not considering drag. So nothing is going to accelerate it horizontally. But the reason the ball falls is because gravity is going to accelerate it vertically. So I can figure out, using the second kinematic equation, the vertical, using the fact that gravity is going to pull it down, knowing the component of vertical velocity, the time it's going to take for it to drop. So that's kind of the next equation we're going to set up. So I'm going to write it just in terms of vertical components. So that's y final equals y initial plus VIY. So again, initial vertical velocity. I have to do that because these are vectors. I have to consider their components. Time plus, if I do this, so this is where we talked briefly about the direction of gravity that I'm accounting for, where I'm accounting for it. And because I wrote gravity as positive 9.81, here I'm going to do plus negative g, so minus 1/2 gt squared. Now I could account for that a different way. If I had written gravity as negative 9.81, then this would be plus 1/2 gt squared. I need to account for the direction somewhere. It doesn't technically matter where I account for it, just as long as you only account for it once. If you account for it in both places, the negative signs cancel out. You actually lose your direction altogether. So account for it somewhere, just once. This is 0. This is 0 because it's going to, it's launched from the ground. It's going to hit the ground again. So if I solve the equation, VIY is going to equal, then the t's cancel, I get 1/2 gt. And then for the same reason, the x component of the velocity was multiplied by the cosine angle. The y component will be the sine angle. So VIY, this is going to then equal VI sine theta equaling 1/2 gt. I'm actually going to solve this for t, for time. So I'm going to multiply the 2 to the other side, divide gravity. So my time is going to equal 2vi sine theta divided by g. And this is the time I'm going to plug into this equation. So that gets rid of the one unknown that I didn't know. Now I can solve for theta, right, in theory. We're going to need to do one more step, but that's the idea. So vi cosine theta equaling delta x over t now becomes delta x divided by 2vi sine theta, and then it would be a double denominator for that g. Remember, if I have a denominator divided by a denominator, or a denominator in a denominator, it becomes a numerator. So g comes up here. And then I want to get theta. That's the thing I'm solving for, which is, again, you can probably start to see where that trig identity is going to come in. So I'm going to scroll this down here a little bit. I'm going to multiply everything to the other side. So this is going to become 2vi squared cosine theta sine theta as equal to delta x g. And then I'm going to move this to the other side. So cosine theta, I'm actually going to leave it like with the 2 actually. So I'm going to divide the velocity squared to the other side. 2 cosine theta sine theta is equal to delta g, oh, sorry, should be delta x, my bad, x g over vi squared. That should be everything. Yep. Okay. This is the trig identity. So we can kind of see it right up here. There's a trig identity that I can expand it to. So this is equal to sine 2 theta. That's equal to delta x g over vi2. We're running out of space, but you can kind of see what we're doing here. The way I then undo any trig identity is to take the arc or inverse of it. So if I want 2 theta, I have to take arc sine of both sides. So 2 theta is going to equal arc sine delta x g over vi squared. I'm going to divide the 2 at the end. So theta is going to equal 1/2 sine of delta x g over vi squared. Now, if we've done this correctly, the units will cancel out perfectly inside the sign operator, I will actually end up with no units left. And so that's going to be a good indicator how you know you've done it correctly, because there shouldn't be any units inside that operator. So for our answer, this is going to, theta is going to equal 1/2. This is arc sine. The change in position was 12.71 meters times 9.81 meters per second squared divided by 12 meters per second squared. You'll notice the meter times the meter per second squared ends up being meter squared per second squared divided by meter squared per second squared. So it looks like everything cancels out. When I plug it in, I get something like 29.99 degrees, which we can round to 30 degrees, which means for this ball to travel 12.71 meters with that velocity, it needed to have been launched from 30 degrees above the horizon.